A couple of months ago, I did a review video for the KC761, which is a combined gamma-ray spectrometer and PIN diode detector. It is claimed that the PIN diode detector of this device can perform alpha and beta particle spectroscopy. In my review video, I tried to test the alpha particle spectrometer, and two things became obvious. Firstly, the results I was getting were not as I had expected, and secondly, that I would need to learn a lot more about this subject. I spent some time reading papers related to alpha spectroscopy, and bombarded the manufacturer of the product with a long series of questions. And in the end, there was one simple question that I just could not find a concise answer for. So I turned to the forums. I figured it was better to just ask the experts. Hi guys, I'm new here. I have a simple question about alpha particles and energy. Is the energy of an alpha particle due to its velocity?
I'm afraid that the answer to that question is not so simple. Perhaps you should be asking this in the high school forums instead.
What the professor means is that you clearly don't even know what the Bethe equation is, so you won't be able to understand the answer we give you.
Oh, I assumed that this was a half mv squared type of thing.
Oh my, you really don't understand. What is the topic of your research?
I'm doing some research for a YouTube video. Well, it seems that there are no adults in that room. Perhaps it's time to finally try out an artificial intelligence-based system, and see what the hype is all about. The papers I read didn't really help me to answer my basic question, and even Wikipedia was pretty vague, so I wasn't terribly confident in finding anything useful here either. But given that I had nothing to lose, I gave it a try. Well. A room full of smart people, but I need a damn robot to give me a straight answer. How ironic.
Phew. Looks like we got rid of that idiot.
I am invincible!
Oh, go and get fucked. Before getting into the meat of this subject, I would just like to recap some of the most basic aspects of gamma-ray spectroscopy. I think that by contrasting the differences, it will be easier to understand this. When we talk about the energy that photons carry, there is one, and only one property that determines just how much energy each photon has. When the application of these photons is radio, we call this energy property the photon frequency, and measure it in units of hertz. If these photons happen to be rays of light, then we usually talk about the photon's wavelength and measure it in meters. Nuclear physicists use another unit for this photon energy, called electron volts. All of these units are directly equivalent to each other, and just like miles and kilometers, they can be freely converted between units with simple linear terms, and sometimes, the odd constant added just for fun. In fact, on a gamma-ray spectral plot, we could use any unit that describes an amount of energy. It is equally valid to use units like kilowatt-hours, joules, or watt-seconds. In fact, you could describe a photon's energy in terms of British thermal units or even megatons of TNT. Gamma photon emissions occur at specific characteristic energy levels, depending upon the decay event that caused it. This is how a gamma spectrometer can be used to identify isotopes based upon their energy fingerprint. The distance between the source and the detector does not change the specific energy of the photons, it just changes the amplitude of that specific energy line. As you detect from farther away, the plot line just moves down to lower amplitudes. Now, I want to talk about alpha particles and their characteristic energies. Unlike photons, alpha particles have mass, and as such their energy is defined by their mass and their velocity. The simple equation for kinetic energy, half mv squared, almost perfectly describes the energy that this particle has. I do need to specify clearly though, that because these particles are ejected from their parent nucleus, at around 5% of the speed of light, general relativity will also play a small part in defining their exact energy. That said, at these speeds, the discrepancy between Newton and Einstein will be around 0.1%. When an alpha particle interacts with matter, it will slow down. This means that the further it travels through a medium, such as air, the more it will slow, and thus its energy will drop. So for alpha particles, losing energy results in the peak moving to the left as well as down. Anyway, that is enough of the basics. Now we can get this alpha particle spectrometer ready for use. The pin diode detector is on the back of this instrument, and is apparently sensitive to alpha particles. In the form that it is shipped in, alpha particles will not be able to be detected by the instrument. The polycarbonate security label is just too impervious to alpha particles and needs to be removed. Once you have removed this label, according to the manual, you have invalidated the product warranty. Frankly, that is absolute bullshit. The pin diode detector is a published feature of the product, so it seems like a pretty shitty thing to ask a customer to accept. Ho-hum, let's push on. Given that my product is no longer under guarantee, I figured that perhaps I should just try to improve the pin diode sensitivity. I'm just going to try and remove as much stuff as I can between the diode and the outside world. Let me just show you the physical structure of this sensor and the product enclosure. This is the PCB that the pin diode is mounted to. There is a EVA pad underneath it, but this does not affect the sensitivity at all. This is the enclosure of the pin diode. And here is the actual chip. It is totally exposed, as the diode package is not fitted with a glass window. Then there is an EVA foam sheet, with 9 small holes punched through it. Here is a very thin sheet of metallized mylar film. This is used to provide the light proofing for the diode. As we will see later, this 5-micron thick sheet has an effect on the alpha particle energy. And finally, we have the outer enclosure of the product. This has the same 9 small holes punched through it. In total, the distance between the sensor and the outside world is 5 millimeters. This might not sound like a lot of air to cross, but for an alpha particle, it's like crossing an ocean. I noticed that the holes in the EVA sheet did not exactly match up with the holes in the main casing, and this was blocking the majority of the alpha particles, which resulted in low count rates. I cut the entire center section out of the EVA foam piece. Then I cut a similar size and shaped hole in the main enclosure. There is slightly more light sensitivity in the new configuration, but under normal lighting conditions, the count rate is 0. But now, with an americium-241 sample close to the detector window, I am seeing just over 1000 counts per second, which is frankly a fantastic level of sensitivity. I need to be sure to protect the delicate sheet of mylar. Perhaps I will make a 3D printed cover for this. I could use the screws for the belt clip to secure it. The first thing I need to be sure of is, am I actually measuring alpha particles? I'm using a piece of paper to shield the pin diode detector from the source, which is americium-241. If these were gamma rays or beta particles, this sheet of paper would have almost no effect. As you can see, adding just a piece of paper causes the count rate to fall from about 120 counts per second to 0. Okay, time to get some actual alpha spectroscopy done. I'm going to be using americium-241 as the source of the alpha particles for this experiment. This source comes from the ionization chamber of a commercial smoke alarm. It isn't a particularly bright source, but it is the best that I have. In this experiment, I am going to collect the spectrum of the alpha particles at various distances from the source. Hopefully I will be able to see how the velocity of the alpha particles, and hence their energy, falls as they travel through the air. I measured the alpha spectra at distances between 5 and 26 millimeters from the source to the actual chip of the pin diode. For each measurement, I waited until a fixed number of counts had been seen by the detector. This meant that each measurement took progressively longer as I moved the detector away from the source. I did this to try and equalize the height of the energy peaks at the distance intervals. I collected the raw spectrum in CSV format, and then plotted this data. Later I applied exponential smoothing to the curve. Exponential smoothing isn't the ideal method, but for these tests it was probably good enough. When we plot all of the spectral datasets together, we can see how the energy, and hence the velocity, is decreasing with the distance. This confirms that the pin diode detector is indeed capable of alpha spectroscopy. When I plotted all of the energy peaks versus their distance from the source, I noticed that if I extrapolated the plot all the way to zero distance, the maximum energy at the source was going to be under 2.5 megaelectronvolts. When I looked up the typical shape for an americium-241 energy curve versus distance, I was even more confused. The flattening out of the curve at the top would put my peak energy level at only 2.2 megaelectronvolts. The source of my confusion is the published alpha energies for americium-241. This is quoted as being 5.486 megaelectronvolts. So why is my measurement so low? Is this a problem with the calibration, or perhaps this is a fundamental problem with this instrument? So, I found this video on YouTube, on a channel called Stoppi. In this video, they create an alpha particle spectrometer, using little more than a photodiode, an op-amp and a biscuit tin. Perhaps the secret sauce is the brand of biscuits that used to reside in this tin, but in any case, the results were pretty impressive. In this test, the americium-241 sample is about 10 mm from the photodiode, and the MCA software is showing a count rate of just over 300 counts per second. This is in almost perfect agreement with my result, of about 1000 counts per second, from half the distance away, once you account for the inverse square law. So far so good. But what the fuck is this? How in almighty God are you getting a spectral peak at 5.486 megaelectronvolts, when the source is 10 mm from the detector? I decided to take another look at that Wikipedia page. It seems that there is a standard for the manufacturing of the americium-241 buttons. The dioxide form of this radioisotope is first mixed with gold. I assume that this is done because of the low chemical reactivity of gold and also to ensure that the resulting alloy is soft. Then, a layer of silver is placed on the back of the slab of alloy, and a foil of gold is placed on the front. Next, this whole sandwich is hot pressed into a thin film, in which the radioactive alloy is 500 nanometers thick, and the gold front cover is 1.5 microns thick. This made me wonder, what other materials must these alpha particles pass through in my measurement setup? How do I figure out how much energy is lost as these particles travel through the various media? I found out that the NIST website has a really cool database and an online calculator that can help me calculate the stopping power of various materials at different alpha energy levels. So, I looked at all the materials that are between the americium-241 source and the pin diode detector, and I found out that even seemingly insignificant things can have a large effect. For starters, there is the 1.5 micron layer of gold, and this part is very significant. Then there is 5 millimeters of air. Next, is the 5 micron mylar film. And finally, I will also account for the 100 nanometer aluminium deposition layer that is applied to the mylar film. Now, we can look at each of the materials in turn, and calculate how much energy loss can be attributed to each one. Starting with the gold layer on top of the source, we can see that this accounts for 1 megaelectron-volt of energy loss alone. The 5 millimeters of air contributes 1 megaelectron-volt of energy loss to our measurement budget. The mylar film also contributes 1.2 megaelectron-volts to the total energy loss. And finally, there is the aluminium deposition on the mylar film. This only contributes 15 kilo-electron-volts to our budget. Okay, so let's add these energy losses up. We have 1 MeV from the gold layer on the source. There is another 1 MeV from the 5 millimeters of air. The mylar film adds 1.2 MeV, and the aluminium deposition layer is basically negligible. So, from the total initial energy of an alpha particle from americium-241, we need to subtract 3.215 MeV of losses, which results in a measured energy level of 2.271 megaelectron-volts. And this is remarkably close to what I actually measured using the KC761. So what about that Stoppi video? Well, I suspect that the creator didn't want to bother the viewers with the complications of this subject, and just calibrated the measurement to a value that was fitting the expected result. It does kind of make the measurement itself completely pointless. If you are just going to fix the results, why measure anything at all? In this experiment, I want to test a couple of materials that are commonly used in the field of alpha particle detection. This is a sheet of 15 micron mylar film. What I am going to do is to see the effect of placing this between the source and the detector. I have stuck the mylar film over the pin diode detector, and when I remove it, you will be able to hear the count rate significantly increase. Although the difference in the count rate is only about 3 to 1, there is a dramatic change in the energy spectrum. I was actually quite surprised by how significant that this difference was. Especially, given how extensively mylar films are used in alpha detectors. Mica is a naturally occurring mineral that is often used for making the windows of Geiger tubes. When this film is placed between the source and the pin diode detector, the count rate falls off to almost zero. This mica film is totally opaque to alpha particles. It seems that the commercial GM tubes that are sensitive to alpha particles must have very thin mica windows indeed. I did a little research, and I learned that there are in fact 20 different types of mica that can be commercially bought. Even small geological differences can result in mica that has quite varied properties. Because mica is quite detrimental to the energy spectrum of alpha particles, typically, it is only used in lower-cost GM tubes. Here is the world's cheapest GM tube that is capable of basic alpha particle detection. It has quite poor sensitivity to alpha particles, so any instrument that uses it is likely to be pretty cheap and nasty. Okay, so what device is this then? Of course, it's that fucking Gamma Scout product again. Or, as we prefer to call it on this channel, the piece of shit. I thought I would see what results I could get from this pin diode detector, with some of my other test sources. This is a sample of uranium ore, and given that uranium-238 has a half-life of 4.4 billion years, it is not likely to have much of a detectable alpha spectrum. Here, I am testing if the count rate is affected by having a sheet of paper placed in the path of the detector. As expected, it didn't make any difference. Next, I am going to place an aluminium block in the path of the detector. If the detected particles that I am seeing are beta particles, then these will be blocked. And indeed, they are blocked. This means that the pin diode detector is also sensitive to beta particles. Whilst uranium-238 is an alpha emitter, many of its decay chain products are beta sources. This is where the detected beta particles are coming from. Here, I am testing a sample of radium-226. This isotope is actually in the uranium-238 decay chain, so it just has a shorter path to a stable form of matter. Once again, I can show that there is almost zero alpha radiation. With the strip of paper blocking the detector, there is no noticeable difference in the count rate. Again, the count rate drops to about 0 when I cover the detector with this piece of aluminium. What I really like about this pin diode detector is that it is pretty insensitive to gamma rays, and so it gives this instrument a powerful way to probe the radioactive world around us. First of all, I want to say that this video has taken the longest time to create of any that I have produced. I have spent 3 months experimenting, learning and researching. There have been some horrific failures, some embarrassing moments and even a couple successes. So, having invested the time to learn about this feature, now what do I think of the pin diode detector of the KC761? My first impression is that this is not a product feature for people that have no time or patience to learn new things. If you want to use this feature, be prepared to seriously hack the device, and hope like fuck you don't break it in the process, because you are not going to be covered by any warranty. I have also realized just how good the hardware design of this feature is. The noise levels are so low that it is easily more sensitive than any Geiger Muller tube-based alpha particle detector on the market today. And my last thought on this feature is this. Alpha spectroscopy is not a point-and-click process. Every step needs to be thought out, researched, planned and then executed. Do not expect good results to come easy. Okay, so what is next for this project? I am seriously considering removing the pin diode from the KC761 and placing it in a vacuum chamber. Perhaps if I put SMA coaxial connectors on each end, and use good quality shielded cables to connect this up, then maybe the current low noise levels can be maintained. I just need to be able to find a low-cost vacuum chamber solution. Thank you for making it to the end of this video. It is the longest one I have ever made. This rather wonderful item is a 45-year-old Chinese People's Liberation Army Type 75 Geiger counter. I bought this device for several reasons, but one of them was because it contains a very strong beta particle source. This Czech source is made from strontium-90.
Unlocking strontium-90 source.
Anyway, that is all I have for you today. I hope you enjoyed my little video, or at least found some parts of it interesting. If you want to see more of this kind of video, you could always press the subscribe button. This is not a commercial channel, nor will it ever be, so I can say what I want, and YouTube's algorithm can go and get f***ed. Thank you for your time.